Welcome to homework.
Okay, the first thing we have to do is name our reactant. Okay, well, we have a 6-membered ring and no other higher priority functional group, so we know that this is going to be cyclohex in the root name. We notice also that we have a double bond, which means this is going to be a cyclohexene. And as is customary for cyclic alkenes that have no high priority functional groups, the numbering scheme will be such that we number one side of the double bond 1 and the other side 2. So we can either go 1, 2, 3, or 1, 2, 3, 4, 5, 6. Right, so we're either going to have an ethyl group on carbon 1 and a methyl group on carbon 3 if we use the red numbering scheme, or we're going to have a nothing on carbon 1, an ethyl group on carbon 2, and a methyl group on carbon 6. And we want to pick the lowest possible numbering scheme, so we'd much rather use the red numbering scheme where we can have 1 ethyl and 3 methyl. And while we're at it, now we know we have a 1 ethyl, so we can say somewhere in here is going to be 1 ethyl. I'm going to write out the component parts. We know we're going to have a 3 methyl. We don't know in what order or where exactly they'll appear, but we do know these will be part of our name. And finally, we've also established that our alkene, our double bond, is between carbons 1 and 2, so this will be a 1-alkene or cyclohex-1-ene. Right? At this point, we have our component parts, and what's left to do is alphabetize the functional groups, ethyl coming before methyl, so that altogether we have 1 ethyl, oops, forgot my dash, 1 ethyl, dash 3 dash methyl, no space between the final functional group and the root name, which is cyclohex, dash 1-ene. And that looks like the final option 4. Yep. Okay, so we've named our substrate. Now we can go on to completing the reaction. Okay, so we're reacting this with HBr. Okay, and the reaction of alkenes with HBr is that we so-called add HBr across the double bond, and there are 2 ways to do this. We can add HBr across the double bond in which carbon 1 gets hydrogen and carbon 2 gets bromine, or we can add it such that carbon 1 gets bromine and carbon 2 gets hydrogen. So let's do the 2 ways that this could go. We get a bromine there, right? Or we get a bromine here. And then the final option is that because this reaction proceeds via a carbocation intermediate, it's possible that we get a so-called hydrogen migration or hydride migration, in which case we would end up with hydrogen on the carbon which bears the methyl group. Like so. So there's 3 options. Okay. Well, note that when we're doing these reactions, that bromine will always end up on the more substituted carbon, right? When you add HBr across an alkene, you get bromine on the more substituted carbon, which in this case is carbon 1. And in order for bromine to end up on the methyl group, we would have had to have proceeded through a carbocation in which we had a positive charge on carbon 2, which is not likely to happen for the same reasons that we end up with our bromine on carbon 1, because the mechanism, if you recall, for this reaction looks like the following. The double bond opens up to grab hydrogen. Oh, and so what I mean is that this is the final answer. If that's all you care about, there's your answer. I'm just showing the mechanism here to explain why. Okay, so one side gets the hydrogen, the other side gets the bromine, right? Or sorry, gets a positive charge. So we're going to put the positive charge here on the tertiary carbon because that's more stable, right? Which is why we won't end up with either of the other options, because both of those options would require instead putting the carbocation on carbon 2 and the hydrogen on carbon 1, which is far less stable and harder to do. Right. And then finally, to finish this reaction off, the bromine adds to carbon 1, which is how we get to that structure.